So we've been studying techniques of integration, and in the last video we looked at a very general sort of integration technique called change of variables or U substitution. And in this video we're going to look at another very general technique called integration by parts. Now before we get into the detail of integration by parts, I want to talk a little bit about something called the differential. The differential is the thing in the integral that is the d whatever. So for example, when we introduced the integral and the dummy variable was x, we had this quantity dx. This is a differential with respect to x. And we really didn't pay a lot of attention to it. But now we want to be a little more careful because it's going to come into play when we do integration by parts. You notice, for example, that when we did change of variables, we had something like f of u times du. And the question is, well, what is this differential? What does it represent? We're going to try to understand it by looking at what dx is, because that's something that we have a little more familiarity with. So if we think about how we define the integral, we said, okay, if we want to look at the definite integral from a to b of f, what do? Well, we divide that interval up into subintervals of length capital delta x. We sum up the area of the rectangles under that curve. And then in the limit of capital delta x going to 0, we get dx. And this gives us a way of thinking about what dx is. Dx represents an infinitesimally small change in x. And so we're going to use that concept to now derive what du is. Now remember, when we were looking at u, we were thinking of u as some function of x. We were thinking of it in a change of variables sort of way. And if we use that same interpretation of dx for du, then we're going to define du as being some infinitesimal change in u, some arbitrarily small change in u. And we're going to start our derivation by looking at what just any general change in u is. Okay, so we're going to call this capital delta u. It's just a change of u as x goes from x to x plus capital delta x. And I'm going to write the first term using Taylor's theorem. So Taylor's theorem tells me that this first term can be written as u to the x plus u prime c times delta x, where c is just some number between x plus x and x plus delta x. Okay? And of course I'm going to have this minus u of x. And I see what's going to happen. These u of x's are going to cancel. And so I'm left with capital delta x as just being the derivative of u evaluated at c times delta x. And if we suppose that the derivative of u is continuous, then as I make delta x smaller and smaller and smaller, the change in u should get smaller and smaller and smaller also, right? So this kind of makes sense. Of course, we know that as capital delta x goes to 0, we get dx here. Okay. And notice by the squeeze theorem, as delta x goes to 0, x plus delta x goes to x. Therefore, c also has to go to x. And since the derivative is continuous, it follows that u prime of c must converge to u prime of x. And this gives us our first important result about differentials. It tells us that the differential of u can be written as u prime, or the derivative of u with respect to x, times dx. Okay? Sometimes people kind of write this in a cheating way. They write it like this, and they multiply both sides by dx, and they get this formula. And even though the symbols can be manipulated algebraically like this, it's really not the correct way of doing this. The second important result about differentials is that if we integrate a differential, so suppose we take equation 1 and we integrate both sides, well, the integral of du is equal to the integral of the derivative of u. And we know that the integral of a derivative gives us back the original function. And so we find out that the integral of du is equal to u. And that's another important fact. Okay, now we're ready to tackle the integration by parts formula. It just says that the integral of u dv can be written as u times v minus v du, of course assuming that all of these integrals exist. And so we can prove this quite easily, actually. If we start off with the differential of u times v, it's equal to v times du plus u times dv. This follows from the chain rule of derivatives, if you want to do it the cheating way. Okay. And now if we integrate both sides, okay, the integral distributes across the terms on the right-hand side, and the integral of the left-hand side just gives us uv. This is by our rule number 2. And now we go ahead, we solve for the integral that we're interested in. And voila, we have the integration by parts formula. Now how do we use it? Well, this is where understanding what the differential is comes in handy. If I go back now and I look at u dv and I write the differential dv as v prime dx, I notice that I'm going to use integration by parts when I have an integrand that can be represented as the product of two terms, one of which is the derivative of some function. And then the formula follows in a straightforward way, assuming as long as the integral of v du is easier to do than our original integral, then we should be able to use integration by parts successfully. Now this kind of raises the question that, well, what should u be, what should dv be? And fortunately, there's a really nice set of rules we can use. These are some functions that we can order. This is called the Lyari Rule. And it says whichever function comes first on this list should be u. The way I remember it is I remember it in reverse. I start off with exponentials, then trigs, then algebraic, then inverse trigs, then log, and I add a capital D here. And I call it the detail rule. And basically it says whatever function comes first on this list is dv. I find this a little easier to remember because detail is an easier to remember acronym than Lyati. Let's see how this works. I'm going to go ahead and apply the detail rule here. Here's some integrals that we can evaluate with integration by parts. First integral is x to the n times e to the x. So what do? I go to my list and say which comes first. I have an exponential and algebraic. The exponential is first on the list, so that must be dv. And of course x to the n is u. And when I substitute these into the formulas, I get the boxed result, which you should verify. Notice something interesting. The integral that I get for v du still has a power of x times the exponential. However, the power of x has been reduced by 1, which means that if I keep on applying integration by parts, eventually I'll wear down x to the n until it gets down to x to the 0. Which will be 1, then I'll be integrating an exponential, which I know how to do. Let's look at the next example, which is x to the n times natural log of x. I go to my chart, which comes first? Well, I have an algebraic and a log. The algebraic comes first, so this must be dv. Okay. Plug these into my formulas, and I get the following. And I can see that the v du integral will be easy to do. I can obviously do that one. Okay, let's look at the third one. And by the way, you can pause the video and verify these things, and I would suggest that you actually do that. If we go to the third example, x to the n times cosine x, I go to my list. Well, I have a trig function and algebraic. The trig is first, so that's my dv. Plug these into my formulas. I get the following result. shown in the box. Now notice that the same comment that I used for the first example applies here. I still have a power of x times a trig function. However, the power of x has been reduced. So by continually applying this method, eventually I'll wear that exponent down until it's x to the 0. Then I'll be evaluating the integral of a sine or a cos, which I know. The last example is the most interesting. It's the integral of cosine x e to the x. Okay, I go to my list. I have a trig and an exponential. Exponential comes first, therefore that's dv. I use the formula and I get this result right here, which is nice, except for the fact that I have an exponential times a trig function I still have to integrate. So what do? Well, I do integration by parts again. Again, exponential comes before trig, so the exponential is my dv, and I integrate that, and I get this result. Now let's look at what we have. Let's put this together. I have that the integral of e to the x cosine x dx, well, the first term here was e to the x cosine x plus this integral of sine x times e to the x, but I figured out that that was e to the x cosine x minus e to the x cosine x integral of. Notice I have the integral on both sides of the equation, so I can solve for it. When I do, I'll end up finding that e to the x cosine x dx is equal to e to the x times cos x plus sine x divided by 2 plus c. So this is a very unusual sort of way of doing integrals. I'll show you two more nice results. This is a result that we get when we're integrating by parts, where we have one of the factors being a polynomial of order n and the other is a function we can easily integrate. And we notice that this formula tells us that, what do? Well, we're going to have n plus 1 terms, and as we go out in the terms, we keep taking the next successive derivative of p. Start off with p, then p prime, p double prime, p triple prime, etc. The signs on the term alternate. It goes plus, negative, etc. And notice that the other function, the f part, we're basically just integrating recursively. So we start off with f in the first term. The second term we have capital F of 1, which is the integral of f. The third term we have capital F of 2, which is the integral of f2. And we keep on getting these capital F sub n terms recursively. It's a very nice, handy formula. It works out very well when f happens to be a trig function, and of course p is a polynomial. And we'll do some exercises with this. Okay, the last formula I want to do is looking at this thing called the reduction formula for powers of logarithms. So here we want to integrate the natural log of x raised to the nth power. And the trick is to realize that we do integration by parts, where we let dv be equal to dx and u be equal to the natural log of x to the n power. When we take du, it's u prime dx. What is u prime? Well, it's a derivative of u with respect to x. We use a chain rule, n times natural log of x to the n minus 1 power. And we take the derivative of the function inside, which is natural log, giving us 1 over x. And of course, when we integrate dv to get v, the integral of dx becomes x. And when you plug this in, you get the following formula that we have here on the right-hand side. Now notice that, as we said before, we still have natural log raised to a power, but the power's been reduced. And that's why it's called the reduction formula, because I can keep on applying this formula until I get down to basically a constant. Okay, that's all for integration by parts. Next, we're going to study partial fraction decomposition.